Okay, let's get started. Good morning and good afternoon, everyone. Welcome to today's MSc software webinar titled Additive Manufacturing Process Simulation for First Time Right. My name is Eugene, and I'm the Product Marketing Manager for MSc Software, and I will be the host for today's webinar. The presenter for today's session will be Arion. Arion is our Business Development Manager at Simufact, and has many years of experience working in industries like automotive, aerospace, and manufacturing. At the end of today's webinar, there will be about 10 minutes Q&A session. So if you have any questions regarding the presentation itself or with the products, please type the questions down in the Q&A window. We will try to get them answered either during those 10 minutes Q&A session or following the events. Okay, at this point, I'm going to pass the presenter to Arion.
All right, thank you, Ji-Jun. Welcome everybody. Thank you very much for joining our webinar. I'm going to talk today about additive manufacturing and more specifically about process simulation, how simulation can assist with some of the issues and difficulties. I'm going to touch both metals and polymers and composites. And let's just get started. Everybody knows that additive manufacturing, it's opening up amazing possibilities. You can make really just fantastic parts. The one I'm showing here, for example, is fully optimized for certain functionality. But also, it's known that with the flexibility and the way it works, there are issues with it. The machine is very expensive. To make the build work correctly the first time is very, very challenging. So what happened when our leadership started talking to our customers about it, the companies really asked us to see if we could come up with our background as a simulation provider to try to come up with solutions or methods that could assist with some of the difficulties that you have with the additive manufacturing process. So at MSc, a decision was made a few years back to invest in the technology, and the first thing that was done, kind of take a step back and say, well, what are some of the challenges where we as MSc, with our simulation background, can help? And at the high level, you can look at kind of three challenges that we can assist with. First one is distortion. It's known that when you build parts, they tend to bend out, so they might be out of tolerance. During the build, can even happen that the powder scraper collides with the part and damages the machine. So that's one big challenge. Second challenge is, as you build the part, you're building up residual stresses, and that can lead to part failure, cracking, support failures. There's a nice example here. Or during the part performance, you need to take into account that there are already stresses in the part. And then the third bucket is more at the quality. You're creating the material at the same time as you build the parts, and you have to make sure that the material you're creating is correct. It's free of porosities, the microstructure is correct, etc., etc. So all in all, it's often a lot of trial and error, physical builds, and cost time and cost money. So how can simulation help? Well, the first thing is to kind of look at the test-based approach if you have no simulation, and where things can break and where you could then help with simulation. So the test-based approach is shown here. So you go from design to print to pre-processing, you print the part, you do post-processing, like heat treatment, surface finish, you have your final parts, and then you do your tests. What often happens is that as you build the part, something goes wrong. As you test your final part, it might also not be correct. There might be too much warpage, too much stresses, too much porosity, and you have to go back and redo maybe the initial design, the printer pre-processing steps, so a lot of trial and error. A quick comment on the design. No, the freedom that the additive manufacturing process provides also impacts the topology optimization environment a lot. For example, these lattice structures, you have totally different considerations and freedoms now with the topology optimization. We do some work in that area as well, but I'm not talking about that today. Today I'm really going to talk about the process simulation aspect and how that can help you. So where do you insert simulation? You want to be left of print. So you have the simulation of the process itself, and the results of the process simulation can impact your topology optimization. So there is a feedback loop to that as well. But you want to optimize your materials, your processes, and your structure, which then gives you hopefully the first time right build, and your performance of the part is correct. So this is very important, that you do your simulation before you do your printing. I mentioned earlier these different types of issues, like you have distortion, residual stresses, and you also have the material aspect, the quality of the part. And to solve all of that in one simulation is very, very challenging. So what we did is we're going to look at the world of additive manufacturing at 3 different levels. You can look at it at a microscale level, a mesoscale level, or a macro scale level. And what does that mean? If you look at the additive manufacturing process at the microscale level, from a simulation perspective, the correct way to simulate that is with very, very high detail, high fidelity. So moving heat sources, fully transient, mechanically coupled, metallurgical coupled simulations, and this delivers the thermal history and the derived results like microstructure. Now on the vertical axis here we see the speed. These type of simulations at the microscale, they're extremely detailed, so you get a lot of data out of it, but they're expensive. So typically you run these type of simulations on small parts, small sections, small samples. If you want to do full part builds, these simulations tend to be too expensive. So that's why you want to go to a mesoscale or a macro scale. And what happens with these type of simulations is the approach is simplified. Instead of using a moving heat source, you use a layered approach. So in the mesoscale, we have an element layer-based simulation where the element layer can be activated all at once or in sections, so you can still take into account some of the effects of in what direction you build it. You get your thermal, mechanical, and history aspects. These simulations at the mesoscale, because we do include thermal aspects, they're reasonably fast. So they're not super fast, but they're reasonably fast. You get both your mechanical and your thermal aspects. And then we have the third environment, which is the macro scale. It's a very interesting technique because in a lot of cases, if you're just optimizing initially first for distortion and stresses, there's a technology available that you can completely take the temperature aspect out of the calculation itself. And that's done by means of an inherent strain approach. And I'm going to talk a lot more about what inherent strain is and how you calibrate your simulation model for that. But this macro scale approach runs very fast. You can run full part simulations in minutes or a couple hours the most. Then the key is that you want to do all simulations at these different levels and then use information from one domain into the other domain. For example, you do a microscale analysis and you can come up with information that you can then use to drive a macroscale analysis or the other way around. So let's talk a bit more about the macroscale approach and how does that work and how did we get these simulations to run so fast, and then what can you do with it? And I'll show some validation examples to show you that it really works. There are a few key items. The implementation is using a Voxel technique, and it's using this inherent strain approach. These are the two items that make it really, really fast and accurate. And then the third item is it is layer-based, so also that speeds up the simulations. So that's a key benefit. You get very fast simulations. You can do it on full parts. And then I'll show you that you can calibrate these simulations with a simple cantilever test. The results you're getting from these simulations is just the part distortion and the residual stresses. So what's this Voxel technique with the solid fraction? You see an animation playing here where, if you look closely, you see that the part itself is simulated using a stack of cubes, and these are the voxels. The part is represented by an outer surface and is completely encapsulated by the voxels. So the software then calculates the interaction or intersection between the part surface and the voxel mesh, and that gives a solid fraction. So during the simulation, the software knows how much of the voxel elements are actually filled or covered by the part and takes that into account during the calculations of stress and strain. The second key item in the macro scale approach is the inherent strain. So the inherent strain, they include the history of plastic strain, thermal strain, creep strain, phase transformation strains, and they embed or encapsulate the material that you're using, the manufacturing parameters, but also on what machine you build it. And I want to point out that these inherent strains, they are orthotropic by nature. It's just built in. So how does that work? How do you come up with the inherent strains that characterize your machine, your process, your material, your process parameters? What you do is you just build cantilever beams on your machine. You build these 3 cantilever beams, one in the X direction, one in the vertical direction, and one under an angle. And then you cut the cantilever beam through the center, and because of the stresses build up in the part, they will bend upwards, and you just measure the tip displacement. So you have a measurement here, measurement at the vertical one, and a measure at the tip of the angled cantilever beam. And again, you build this one time on your machine with your powder, with the settings that you want to use to build parts. Once you have done this build of the cantilevers and you have the tip displacements measured, you plug this in the software, you enter those 3 measured tip displacements, and then the software will fully automatically run through an optimization a loop to come up with the inherent strains that characterize your process. And once you've done that, you store these inherent strains in your database, and you have characterized your machine for part manufacturing. Then you can use that information to start running simulations. So now you can run a full part build like this in Disk, and you can look at the distortions and the stresses, and then you can follow it up with a heat treatment simulation, removal of the support, hipping, that's all included. And these simulations then run very fast because of the inherent strain approach that we use. Now, in this simulation, I showed you both the part build, which gives you the distortion and the stresses, but it also showed that you can follow it up with a heat treatment. So let's talk a little bit about that step. The heat treatment that's implemented, of course, it requires you to define the temperature versus time curve. When you do a heat treatment simulation, the material properties, they will include the material properties as a function of temperature. So the elastic modulus, Young's modulus, the flow stress, conductivity, all has to be defined as a function of temperature. And the software comes to the library that include all that information. Now, how do we do the stress relief during a heat treatment? We take into account the creep of the material. So we have creep laws for that. And the question might be, well, is that sufficient? Is it sufficient to calculate just the creep effect during a heat treatment? And the answer is that yes, for a large part it is, because creep is really the crucial factor to achieve stress relief during a heat treatment. And then in addition to that, there's more going on during a heat treatment than just a creep. But if you want to include that, we do run a fully transient simulation, so you can plug in additional simulations to take into account other metallurgical effects. And then there's another aspect to the process chain of additive, and that's the hipping, so hot isostatic pressing. To simulate this, you not only need to input temperature versus time, but you also need to provide a pressure versus time that the part feels. And in addition to temperature-dependent material properties and the creep laws, now there's also a densification law. It's a power law where the density changes as a function of the pressure and the yield stress. So during the hipping process, in a way, it's just another heat treatment of the part, and that can lead to further stress relief and distortions. And that's one of the key reasons you want to include this in your simulation, because having the distortion at the end of just the build or is not sufficient. You need to have the distortion and the stresses after your heat treatment and your hipping process. And then in addition, because we have the power law for the densification, you can also look at the densification of the part, how the density is changing, which will give you an indication if your porosity is at the right level. So I talked about the macro scale approach with the inherent strain. The inherent strain approach, it's not something new. It's not something that we invented. It was already in use for decades by the welding industry. But it's the first time that this technology has been applied for additive manufacturing simulation. And I want to show you a few validation examples to prove that this technology really works. Well, we're a simulation company, so we don't actually build parts ourselves, but we work very close with large institutes, research institutes. For example, Fraunhofer Institute in Germany. We work very close with them to do some validation of the technology. So Fraunhofer, they built this cantilever beam, cut it, and then we calibrated it, and we could show that indeed by using the inherent strain, you can very accurately correlate the distortions to the measurements. Simulation time here is only 3 minutes. Second example, also done with Fraunhofer Institute. It's a double cantilever beam. This was very interesting because the part was built. Then after build, it was cut on the right side you see a lot of distortion because of the stresses. Then it was heat treated, and then it was cut on the left side. And you see that it was indeed a lot of stress relief, very little distortion. And again, the simulation correlated really well with the experiment. A third example that was done together with Fraunhofer Institute was an aircraft bracket made out of aluminum. The part was built and was simulated. The simulation time at that time was about 20 minutes. Today we run these in 5 to 10 minutes. The distortion, again, was captured very, very accurately. So these were some nice examples. Another example that we did together with one of our partners is NTT Data in Japan. They built a very interesting part out of titanium. It's a thin-walled bike frame part. And it's known if you additively manufacture thin-walled structures, you have a tendency to get some distortions. So that was, again, the objective of this study, to see how well can the simulation with the inherent strain capture those type of distortions. And here are some examples. So this should be circular, but it's oval, was correctly captured by the simulation. Here, also some distortions where it bent inwards was correctly captured. And then on top of it, there was a failure of the support structure. And if you look at where the stress hotspots are, was also correctly captured by the simulation. And in this area was some buckling phenomena along this curved line, which was also captured by the software. So these examples show that you can capture quite a lot of detail of the distortions with this approach. Up to now, I showed you only examples of metal, titanium, aluminum, but this exact same technology of using inherent strains to predict distortions and stresses also works for polymers and composites. Here I'm showing you an example that was done together with Solvay. This is a part built with a Sinterline powder, which is a glass bead reinforced polyamide. This part was built in the machine, and the normal distortion was measured, and that's what's shown here in the picture. It was simulated, and again we got very accurate correlation between the simulation and the experiment. And also, if you look at the occurrence of a certain level of normal distortion, the counts, the histogram shown here, also correlated really well. So this technology for using the inherent strain with the voxel elements, layer-based, can be used for both metals and plastics. So this is my first kind of summary slide, that the macroscopic approach can give you a very fast and accurate prediction of distortion and residual stresses, and you only need a simple calibration with cantilevers to come up with the inputs for those type of simulations. Now, once you have calibrated your machine with the inherent strains, and you have these inherent strains stored in your library, then you can start doing part builds. And what type of things can you do then? Well, you can virtually explore the influence of the different manufacturing parameters and materials, the cutting direction and support removal, that all has significant influence on the distortion. You can look at different build-up orientations. Should I build it vertical? Should I build it horizontal? You can look at different support structure configurations. Can I get away with less support and save material, or do I need a lot of support? And then the process chain. You can study if it's best to build the part by doing a build, then a heat treatment, cutting it from the plate, and then you do a cooling, removing the support, and do a hipping, or should you maybe reverse some of these steps in the process chain? And another example that's really useful to study with simulation is that you can come up with the best compensated shape. So if you build this aircraft bracket, it has a tendency to bend upwards. So what you can do, you can simulate this, and then you can say, well, why don't I build the part downwards? So you export this part from the simulation, you scale the displacement in the negative direction, and then you simulate it again, and it will then show that now you have a much straighter part. So coming up with the best compensated shape for your parts is also possible with simulation. I want to step in a bit more detail through a nice example that was done with polymers. It's a Plenum chamber made out of Sinterline powder. This is a part that was built as as part of an effort to build a complete plastics engine. And the challenge here was that this plenum needs to withstand certain loading. So the study was, okay, if we additively manufacture this part, will it withstand the pressure loading that it feels during operation? Now, in the field of plastics, the software has been used for a long time to come up with the materials of the polymer itself. So the way that's done is you start out with the matrix material, the filler, and the percentage of filler versus matrix. So that's input of a homogenization simulation, which then gives you the global behavior of the stress strain curve. So you have the stresses as function of strain that you can use in a finite element simulation. This can then be captured in equations with the mean field equations, which then can be used in the process simulation or the performance simulation. So these type of things have been done for years. It's nothing new. But now it's being applied to additive manufacturing. So what was done here, using the process that was going to be used to build the plenum chamber, some tensile components were printed, and the material characterization was validated. And indeed, it can be seen that the compressive behavior was captured very well. The tensile behavior was captured very well. What was a key aspect here is that when looking at the failure, it turned out that the failure was very, very dependent on the direction of printing. So also a failure mechanism had to be developed that represents that correctly. And it's shown here that the model used to simulate the material correctly captures the direction, the printing orientation dependent behavior very well. So with the material characterized, the plenum was built, and that's shown in this simulation. So again, you build it, you can look at the distortions and the stresses. I'll let this finish. And once you have the stresses and the strains, then you can continue and do the performance analysis. So what happens here is you're loading up the part, and at any moment during the simulation, there's an interaction with the mean field equations to come back with the stress and stiffness matrix based on the strains that the part feels. And then you can predict what's the load at which the part will fail. So for this study, the part was built in different directions, and I showed earlier that the failure of the material is dependent on the print direction, and you see that back in the load at which the part will fail based on the build direction. So if you build it in one direction, it's actually much stronger than when you build it in another direction. Now, due to limitations of the build chamber, it had to be built in this angle direction, and the simulation predicts that it will withstand 9.1 bars. So a test was done, and the Plenum was loaded up to 6 bars for about an hour at 100 degrees Celsius, and it did withstand that pressure load. So it was a successful test. This part was not yet loaded up to the predicted failure of 9 bar, but that might still be done at some point. So these were some explanations of the technology that can be used to simulate additive manufacturing. And now I want to talk a little bit more about kind of the different products that we offer at MSC. And there's 2 environments. We have one environment for polymers and composites, which is built based on the Digimat software, and one for metals, which is based on the Simufact software. First, a few words about the Digimat environment. So, in the plastics world, you always talk about the material engineering because you're designing the material very often. So this is one field where you can apply the Digimat software, and I'll show a little bit more about that. Then the process simulation. So traditionally you had injection molding. Now we have additive manufacturing process simulation, and then you can carry that all over into part performance type simulations to come up with the stiffness and the failure. And this Plenum example very nicely showed that you can study the strength of the part based on print direction, for example. So this materials performance or materials process and performance, let's talk a little bit about each of those. So the material side is captured as usual with the Digimat mean field, finite element, and the material exchange capability. So you can just determine with this capability what the material properties really are based on the way the material is structured, with the amount of filler versus matrix material and orientations. Then the process simulation. So a new capability was embedded in the ecosystem that the Digimat environment provides, and it's just a very straightforward way to define a process to build a part using the inherent strain approach. And then again, using the existing ecosystem of Digimat for polymers and composites, you can take the results and push it out to all the major finite element codes to do performance studies. And in this example, we show that you have additive manufactured parts, but if you have injection molded parts, it all fits into the same existing ecosystem. A few words about the metal side of things. So the Simufact environment has been tailored for metal manufacturing processes, also an existing ecosystem for many, many years available for metal forming, like forging, stamping, and welding to predict how structures respond to welding processes. And a brand new product was created to now address metal additive manufacturing simulation. And it's key here again to understand that the Simufact simulation covers the process itself, the build part, heat treatment, cutting it from the plate, removing the supports, doing the hipping, the hot isostatic press treatment. But this is embedded in this whole process chain where you can go from topology optimization, hand it off to the Simufact environment to do the additive process simulation and then at the back end, you can hand it off to the traditional CAE tools for stress and fatigue analysis and studies. As I mentioned, a completely new software was developed. It's a great software for doing these additive manufacturing studies. Very easy, very targeted. You set up simulations literally in minutes, and it covers all these aspects of building, heat treatment, support removal, and then looking at your results. And this is based on the Mark solver. So this is a proven solver that has all the capabilities needed to simulate the additive manufacturing process. But then we put this very easy to use, powerful GUI on top that allows you to work in a very workflow-oriented approach. One final comment about microstructure, because I talk mostly about the macro scale approach to do simulations. So that's out today. In Digimat environment or the Simufact environment, we have versions available that you can do macro scale type simulations. In the metal environment, we're coming out soon with capabilities to do at the mesoscale, so you can then look at temperature in your parts. If you are interested mainly in metal additive manufacturing, but then looking at the microstructure, I recommend that you also have a look at the environment from our partner MRL, which has created a complete ICME platform for data analytics, materials modeling, and finite element simulations based on the Simufact framework. So in conclusion, we all know that you can build really amazing structures with additive manufacturing, but the question is, can you reliably print them? What I try to point out in my short talk here is that you really have to simulate the whole process, from building, cutting, heat treatment. You have to include the complete process chain, going from material to process to performance. And you really should be looking at simulating it at different scales: macro scale, meso scale, micro scale, and pick that environment that works best for what you're looking at. And maybe you need to look at all three of them. And then finally, there are new simulation tools available: Simufact Additive for metals and Digimat for the polymers and composites. And that concludes my presentation.